Hey everybody, we are going to talk about section 2 of chapter 3, applying properties of rational exponents today. Remember that anything I write, you need to be writing, and make your brain happy. Color it, highlight it, circle it, star it, put a sticker on it. I don't care. But make your brain happy so that you can go back and remember. Also remember that anytime you do notes, you can use them on quizzes, and that's your reward to yourself for doing a great job. So today, we're going to be simplifying expressions with rational expressions or exponents to find the velocity of a jet. So let's remind ourselves about some properties of rational exponents. Remember this property where we're talking about multiplication of exponents, that when they have the same base, we can keep the base and simply add the exponent. So let's go ahead and do this example. Remember that these are the same bases, 5. So we're going to keep the base. And instead of multiplying the exponents, we simply add them. So 1/2 plus 3 halves in the exponent is 5 to the 1 plus 3 is 4. Because they have the same denominator, we can just add them. And 4 over 2 reduces to simply 5 squared. And to evaluate that, we say it's 25. All right, next one. We're going to go ahead and look at this one. When we've got a power to a power, remember that we simply just multiply them. So again, we've got 3 to the power of 5 halves, all to the power of 2. So remember, when we've got a power to a power, we just multiply them. So we keep the base, take the exponents, and simply multiply them. So we got a 3. Now 5 over 2 times 2 is like saying times 2 over 1. These can cross cancel, so we're left with an exponent of 5. Okay, here we've got our property of some product with an exponent. We can distribute that exponent to each parts of the product. So we have a to the m and b to the m separately. So again, we've got 16 times 9, which is product, and they're both to the 1/2 exponent. So I'm going to distribute them. So this becomes 16 to the 1/2 times 9 to the 1/2. Keep in mind, remember, a 1/2 power is like saying the root or square root of x. So I'm really saying here 16 to the 1/2 is like saying the root of 16, and 9 to the 1/2 is like saying the root of 3. Well, I know that the root of 16 is just 4, and the root of 3 is just, we can't simplify that anymore, so we just say 4 root 3, and that's as simplified as we can. For our next one, remember that when we've got a negative exponent, it's like a reciprocal or a fraction of 1 over. So this negative 1/2 here means that we are going to make a 1 over, and whatever's left goes under the root. So 36 to the 1/2 power. Just like on the last one, remember that a 1/2 exponent is like saying the square root of 36 is in the denominator. Well, I know the root of 36 is simply just, and because we applied the root, remember it's plus or minus, so this is plus or minus 6. So this is plus 1 over plus or minus 6. All right, and then when we've got a division, we're dividing the same base number with powers. We can take the same base and subtract their powers, top minus the bottom. So notice here we've got the same base, 4 and 4. So we're going to keep the base, and now instead of dividing the powers, we're going to take the top minus the bottom power. So this is 4 to the 5 halves minus 1/2 is just 4 halves. We can simplify that to 4 squared, which is just 16. And then this last one here, we've got a quotient to a power. So we can distribute that power to both parts of the quotient and get a to the m over b to the m. So let's do that here. We've got a quotient, and we're going to distribute the power to both parts. So 27 to the 1/3 over 64 to the 1/3. Now let's rewrite this fractional exponent or rational exponent. We know this is going to be a 3 on the index of 27 to the 1. Well, the third root of 27, if you look at your list, is just 3. not a plus or minus, just a 3. And the third root of 64 to the 1, or just 64, is 4. So we're left with 3 over 4. And the last property is, now if we're talking about properties of a radical, if I've got n on the index of a radical of a product, I can separate that product into 2 separate roots. Same thing with this quotient property. If I've got a root with an index of n and I've got a quotient inside, I can separate the quotient with their own roots as well. So let's go ahead and simplify this. Right now they're separated. I've got a separate third root of 12 and a third root of 18. So I can combine these together by keeping that root and multiplying that inside together. Well, if I use my calculator, really quickly I can find 12 times 18 is 216. And if I look on my my x to the third power chart, the root of 216 is not on there. So let's see if we can find any other third roots that will work for this. Actually, hold on. 216 is on there. It's 6 to the third is 216. So I know the third root of 216 is just 6. All right, let's look at this one. We see that both of them have a fourth root on top and bottom, so they have a common index. So we're going to move this and change this. Instead of the fourth root of 80, which doesn't look great, and the fourth root of 5, I'm going to put 80 over 5 in here, which I know 80 divided by 5 is just 16. And I know, well, if I look at my x to the fourth chart that you guys did yesterday, I know 1 to the fourth is 1, 2 to the fourth is 16. So I know the fourth root of 16 is just a 2. And because they started with the root, it's not plus or minus, so we just leave it as positive 2. Okay. Okay, let's talk about what simplest form is. So if they're asking you to put it in simplest form, that there's no remaining perfect nth powers as factors, meaning if you can take a simpler factor and take a simplified form of a root, go ahead and do that. There's also a rule that we have just in math in general, it starts in algebra, that in simplest form means that we have no roots in the denominator. So you're not done with your answer if you see a root in the denominator. You have to keep going. Okay, so let's talk about this. For this one, when we're simplifying this, we're going to say, okay, well, I know that 135 is not on my list of perfect cubes, right? I know 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 60, I believe it's 64. 5 cubed is 125. Okay, we're going to stop right there. I don't see 135 anywhere on this list, but here's what we're going to do. We're going to play around and see if any of these numbers can factor into 135. So I'm going to take 135 and just start just dividing. 135 divided by 1 isn't going to help us, so let's try by 8. That doesn't work. What about 27? 135, does divide by 27. And so what I can do is I can split this up. The third root of 135 is also the same as the third root of 27 times 5. So I can rewrite this and separate that product based on our rule. So we can take the third root of 27 times the third root of 5. And because I know the third power of 3 is 27. So I know the third root of 27 is just a 3. And this gets multiplied. That third root of 5 really can't work at all, so this simplifies to the 3 times the third root of 5. And then for this one, this fifth root of 7. Now, I can't do anything with this. There's nothing that can factor down that will give me anything else here. I don't see anything. 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 I don't see anything Oh, except for, sorry, on your notes, I want you to, it split up my notes, sorry. This should be right here. Here we go. Okay, so not looking at this. Sorry, your notes are different than mine a little bit. So I've got the fifth root of 7 over the fifth root of 8. I notice that both of these have the same index. So I'm going to keep the index of the root and I'm going to put this in here. This is not super helpful because 7/8, nothing multiplied times itself gives me 7/8. So what I'm going to do is I'm going to say, okay, what can I do to make this work? Keep in mind, I've got a fifth root. So I'm going to pull out my list of numbers to the fifth power and see what we get. I know 1 to the fifth is 1, 2 to the fifth is 32, and 3 to the fifth is, let's see, 243. We're going to stop right there because it gets pretty quick, pretty fast. I'm going to say, we know we cannot have a root in the denominator, and this also counts. I can't have a fifth root of 7/8. So what I'm going to do is we're going to say, okay, what can we do? Because if I knew that I had a fifth root of 32, it would work. Is there a way for me to get this 8 to a 32? And the answer is actually, yeah, there is. What we can do is we can multiply everything. So to multiply 8 to 32, I can multiply everything by 4, right? Because 4 over 4 is just 1. So I end up with the fifth root of 7 times 4 is 28 over 8 times 4 is 32. Well, if I re-separate them and I take the root, so I get fifth root of 28 over the fifth root of 32. Well, isn't the fifth root of 32 just 2? And then that fifth root of 28, I don't think anything else can come out of that. So we just leave it the way it is because that's fine. That's legal. We can leave it the way it is. And now we've simplified it so that we can be in simplified form completely. All right, here's another rule. When n is odd, then it can work either way. It's either going to be positive or negative. But when n is even, it's going to be positive, okay? So when n is odd, if these match up, so this n to this n, if they match up, it's just x. But if n is even, so let me erase this. If n is even and these two match up, then the answer is going to be always positive if it's even. So let's talk about this. Because this is odd, we're not worried about it. It's just going to be whatever the value of 5 is because these cancel. And again here, these two cancel, so this is -5. But see how this is 4, which is even, and this is a 4. They cancel, so our answer is the absolute value of 3, which is just 3. And here, we know these will also cancel, and so we've got our value of -3. When we're adding and subtracting radicals, think like terms, okay? So do we have like terms here? So just think about this. Here's fourth root of 10, and look, we see another fourth root of 10. It'd be kind of like saying x plus 7x, but instead of x, we're dealing with a fourth root of 10. So I have 1 fourth root of 10 and 7 fourth roots of 10. I can also like put this invisible 1 in front. So 1 of something plus 7 of something gives me 8 fourth roots of 10. Okay. All right, next one. We're going to simplify this one. So remember, again, we've got two pieces here. They're products. So I'm going to go ahead and simplify them out. We've got the third root of 64 and the third root of y to the 6th. Okay, so now that we've split them up, we're going to look back at our list of anything to the third power. So I know 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, and 4 to the third is 64. So I know this third root of 64 is just a 4. I also know this 3 on the index tells me I'm looking for 3 identical things to pull out of the root. Well, I know y to the 6th. I can rewrite that as y times y times y times y times y. And what I'm going to do here is I'm going to circle up groups of 3. And when I take out this group of 3, those 3 y's are y to the third. The third root of y to the third is just y, and that comes out of the root. Again, this one will also come out of the root as well as just another y. So I end up with 4 times y out of the root, which is just 4y squared. All right, so for this one, I've got a product here, so 27 times p to the third times q to the 12th, all to the 1/3 power. So I'm going to distribute this to each part of the product, and we get 27 to the 1/3, p to the third to the 1/3 power, and q to the 12 to the 1/3 power. Now remember, we can either simplify this or use more exponential rules. We know 27 to the 1/3 is just saying the third root of 27. When I've got a power to a power, I'm really multiplying the powers. Okay, and then q to the 12 to the 1/3, again, we're just multiplying those powers. So let's simplify this. We get the third root of 27, that's just 3, that's on our list. 3 times 1/3 is just 1, and 12 times 1/3 is just 4. So I'm left with 3 times p times q to the 4th. Okay, and then this last one, the index on the root is 5, and we've got a product of 4, 8 to the 8th, b to the 14th, and c to the 5th. So I'm going to break this up into their own individual little 5th roots of each and see if we can simplify this. So we're just giving each its own root so our brains aren't overwhelmed, and we're going to focus on one at a time. This 5th root of 4, we can't do anything. We can't simplify anything, so it's just going to have to stay the way it is. Okay, and then let's look at this one. Remember that I need a group of 5 identical things to come out of this. So if I say the 5th root of a to the 8th, I can say a to the, or a times a, basically 8 times, right? 1, 2, 3, 4, 5, 6, 7, 8. So if I'm looking for 5 of these to pull out, this can become a times the 5th root of, how many are left? A to the 3rd. Okay, so that's another way to, that's one part of simplifying that. This 5th root of b to the 14th, that's like saying b to the 5th times b to the 5th times b to the 4th, right? Because if there's 14 b's, that's like a group of 5, and a group of 4. So I know the 5th root of b to the 5th comes out as a b. The 5th root of this b to the 5th also comes out as a b. And we're left with the 5th root of b to the 4th left. So when I go to simplify this, I'm going to say this is like saying b squared times b to the 5th root of b to the 4th. And then our last part here, the 5th root of c to the 5, those cancel, and it's just c. So what we're left with is, and what you're going to do is everything under the root is going to go together. So this 5th root and this 5th root are going to go together. So we say 5th root of a to the 3rd is in here, and b to the 4th is in here, but everything else is going to get pulled out front of the root. So we say a times b squared times c, and that is our simplification. That's it for today. I will see you tomorrow for our